All right, let's take a look at another sequence. In this one, we have the sequence 2, 4, 8, 16, 32, and so on. We see it in normal format just listed, and we also see it in table format. And it says, what's the next term? So let's take a look. Two different ways we can look at it. We can say, well, from 2 to 4, we can add 2. But does that work for the next one? Okay, if I add 2 to the next one, I don't get to 8. So it can't be addition, right? Which is usually the first thing we want to check. So if it's not addition, what else could it be? What if we multiply by 2? 2 times 2 gives me 4. 4 times 2 gives me 8. Well, 8 times 2 gives me 16. 16 times 2 does give me 32. So this would be our pattern, meaning that the sixth term is 64. So what's the next term? We can say 64. I'm going to write it in two different areas. Then it says, what's the recursive formula for the sequence? So remember that for the recursive formula, you must take a look at the preceding term. So we can say g of n is equal to the term before it. So g of n minus 1. Get my head out of the way. Times, well, what's our pattern? Times 2 when g of 1, our first term, equals 2. Well, let's see if this works. So we take the term before, that's meant to be a 2, sorry, and we get 4. Let's try the next one. We take the term, yep, so this will definitely work. So the recursive formula for this one, for part B, is g of n is equal to g of the term before times 2 when your first term equals 2. Then it says graph the terms of the sequence as an ordered pair. Let's see, 1, and we have to do estimation here. 1 would be at 2. 2 would be at 4. Let's see, 3 is at 8. 4 is at 16. Then 5 would be at 32. So we can see it looks linear, but there is a little curve to it. Then what kind of graph does this form? Okay, so this type of graph is not a linear graph. This type of graph would be considered a geometric graph or a geometric sequence. Also can be called an exponential graph, I believe.